And we're recording, and chapter 21b will be the second part of the blood vessel presentation. And where we're going to begin is down in the capillary bed, because an odd thing happens. We're so used to the processes in our body being balanced. So if there's a certain amount of gas entry, there's a certain amount of gas exit. And when we study the capillary beds, we see that there are two things that are contributing to the molecular exchange that's going on across the capillary bed. Now, coming out of the arteriole, you're leaving a sealed vessel. As you go into the venule, you're entering a sealed vessel, and that net-like complex of capillaries are interconnected to allow blood flow through different tissues. Now, the thing that is contributing to a molecular exchange is filtration and reabsorption. Filtration is the exit, reabsorption is the entrance. And the forces that actually contribute to that exchange are two. What we're going to focus on right here, I mean, we've already talked about the supplies, right? Oxygen and nutrients are being delivered. They're going to be consumed. Carbon dioxide is going to be generated. Ammonia and then later urea are going to be generated as major waste products. And those are source-sink relationships. So diffusion is largely driving them. But it's a little bit different with the water. The water leaves on the basis of two forces: hydrostatic pressure, and that is the pumping pressure, the actual hydrostatic pressure in the capillaries, which basically squirts water out of the capillaries. In addition, there are differences in concentration of solutes on the two sides of the capillary wall, and so osmosis is at work. The condition of the capillary bed is changing from the arterial side over to the venule side as supplies suffuse out into the surrounding tissues and as wastes re-enter. And water is doing the same thing. So together, these control net exchange through the capillaries. Excuse me a moment. Now, the transition point between filtration and reabsorption is actually a little closer to the venous end than the arterial end. And one of the surprising things we discovered about capillaries is that more water leaves the capillary bed than re-enters the capillary bed. And so there's a net loss of water from the bloodstream as we go through the capillary bed. That means that every capillary bed in your body, every single organ system, experiences a net loss of water around the capillary bed. This is where we are introduced to a new system that its first job is to address that water balance, and it's shown here on this slide. Excuse me a moment. Somehow I lost my pointer. Excess fluid enters the lymphatic vessels in every single capillary bed. So this excess water is actually leaching in to the lymphatic vessels that are stationed in every capillary bed. So it's sort of like a little drain. The lymphatic vessels are going to be structured like veins in that they have one-way valves. Once the fluid moves along that, it gets above a one-way valve and cannot come back. And it is the random motions of the body that are squeezing and releasing that are basically moving this lymph from all parts of the body and returning it back to the bloodstream. That's occurring high up here in the thorax. Now we'll deal with the particulars of this fluid exchange in more detail in chapter 22, which is about the lymphatic system. In fact, immunology and the protection of the body through our blood cells and our immune reactions has been so important in our science recently that we often emphasize that so strongly in the lymphatic system that we ignore this water balance issue that is constant and something that has to be taken care of all the time. This is an overall diagram showing you the arterial to venular trip and the basic pressures from filtration and from reabsorption and how they add up as you go across from the artery side to the vein side. Now that's going from, on the left side, arterial, high exit of nutrients, which tapers off as you go to the left. And as you start in the arterial, low diffusion of wastes, which is increasing as you go to the right. You can see that the width of that arrow stem, filtration and reabsorption are not equal, and that this excess, which amounts, what you can see here, 3.6 liters per day, is the flow that is being collected by the lymph system and returned to the cardiovascular circulation. Now, as I said, in this blood vessel chapter, we're not going to return to the details of that. We're going to explain that in chapter 22. But I want to just make a comment about this green vessel. Notice that it's got an end. So this is not a cardiovascular system where things are flowing through on a constant basis. There is no pump. It basically is being moved by the compression and release of surrounding tissues. It basically starts here in the capillary bed. This is the entry point. And then from here, there's a converging system up to the major lymph vessels and sinuses in the thorax and abdomen, which are then collecting larger and larger flows of this clear liquid called lymph. Because this is basically a space that penetrates all parts of the body, because this is moved by milking action, which is intermittent, not constant. In some parts of the body, the lymph pressure can drop to near zero quite frequently. So right in here is a kind of a passive, low pressure, liquid-filled system, and that means that it's a good place to sort of travel through the body. It's also a good place to lounge around. And we find lymphatic cells that are going to have a major role in protecting the body through their active and passive immune responses, of basically taking up posts in lymph vessels. Now, there are places where lymph vessels converge on expanded tissues where we're going to actually organize those cells. B cells and T cells are going to be organized in groups there, and the flowing lymph is going to be carrying through material from around the body. And if there are toxins, if there are pathogens, then this is a way of filtering and fighting those as they flow out of the infected region. So more about that, much more about that later. But for now, we're going to go on to cardiovascular response and think about several things that are common experiences and ask how the body reacts when we go from at rest to exercise. We accelerate our ATP production and consumption, and we're moving our body at greater and greater exertion. What happens? How does the cardiovascular system adapt to that emergency? This should be blood loss, hemorrhage, where all of a sudden we're punctured and our blood is leaking out. What does the cardiovascular system do in response? And finally, the topic of development and growth. Since we all start out as a result of fertilization, conception produces one squishy cell. there clearly is no cardiovascular system. So how does it develop and grow? In what we call the fertilized egg, which quickly goes to the zygote, to the embryo, to the embedded embryo and the development of a recognizable fetus, right up to the point where the cardiovascular system is ready at birth to perform on its own. So to begin with exercise, we realize that we have a tremendous range of muscular exertion. And so we have to have a range of cardiovascular performance that matches that. At rest, we are working on the very lowest output of our cardiovascular system. So what happens when we go from at rest to light or medium exercise? Now, I want to put in a qualifier here. Light to medium means perhaps anywhere from a nice walk around the block to a regular workout that demands higher levels of exertion, or even a work exercise that demands that you contract your muscles at higher level. The first thing that happens is the body can easily dilate the blood vessels and lower the blood pressure. Now, that produces a cascade of effects and autoregulation within the heart, and that immediately increases the cardiac output to match the level of exercise. You know that a brisk walk might cause you to breathe a little harder, whereas picking up hay bales or manually raking the yard might cause you to breathe quite a little bit harder. As this venous return increases, we get Starling's effect, the expansion of the right atrium. With these muscle contractions, we get greater stroke volume and an increase in cardiac output. So this is a normal kind of everyday occurrence because we go from asleep to awake and alert. When we stand, we begin to walk, our blood begins to circulate. This is a normal feature of every day. Now, if you are a fitness buff and you exercise at higher levels, perhaps you have a known routine that involves running or a sport of exertion like tennis. Anything like that, you reach this level we'll call heavy exercise. Now, heavy exercise and cardiovascular response, I'm going to describe the limit of heavy exercise to our maximum aerobic output, meaning we're breathing as fast as we can, we're working our muscles very hard, but all of the ATP production, the great majority of it, is being taken care of by aerobic respiration. We haven't gone anaerobic. We're not going for that final sprint, that final burst of fight or flight. But there is an activation at low levels, increasing as our exercise gets heavier. There is an activation level of the sympathetic nervous system. Now this, we can typically depend on an increase in cardiac output of about 3 to 5 times that level at rest. So it's not unusual for an ordinary citizen to get that level of increase in cardiac output. As this becomes limited, meaning you're exercising heavily enough that you're getting oxygen debt in certain places in the body. Heavy exercise usually means heavy use of your skeletal muscles. So your skeletal muscles are starting to reach a maximum based on the amount of oxygen that is being delivered. This is where the cardiovascular system uses those arterial sphincters and redirects the blood flow to the organ systems that are working the hardest. So at this time, during very, very heavy but usual exercise, like let's say you're out, your normal thing to do on a Monday is to run 8 miles. During that run, you're going to reach the point where your muscles are working so hard and so fast that you're getting oxygen debt. At that point, blood flow to your digestive system, to your urinary system, to your reproductive system is going to be cut down. Not completely eliminated, but a great deal of that is going to be shunted over to the dilated blood vessels that are supplying your working skeletal muscles. The main emphasis under heavy exercise will be the skeletal muscles, the lungs, and the heart. During this time, I also want to make another comment here that's important. We mentioned that our blood flow, 2/3 of our blood at rest, is in the veins. During this time, the whole venous side of the body is using its smooth muscle fibers to contract. That not only increases the blood pressure, but it decreases the capacity of the vein side of our vessels. So that means the venous reserve that we have at rest is completely mobilized, and the veins are actually supporting this increase in blood pressure by a decrease in system volume. And I want to point this out. When you work with fluids and you have a certain operating level, think about the level of your antifreeze or the level of your oil or brake fluid, power steering fluid, all those fluids that are in your engine. One thing a mechanical system does is you fill it up to a certain point and then it's full, and it draws on that pool or that sump in order to supply the fluid to the right mechanical device. Something a living system can do is that it actually can take the volume of that sump and decrease it. So in responding to decreasing blood pressure, we might pump the heart faster, and we might increase the stroke volume. But another thing we can do is actually contract the volume of the blood vessels, and that accelerates the blood even more. Now, one caveat to this decrease to non-essential systems, and this is true all times, waking or asleep, exercising or at rest, emergency or relaxed, the blood supply of the brain is basically unaffected. For the size of the brain, the blood supply to the brain, the blood flow to the brain is relatively high. And it is also relatively constant. This is another feature of our physiology that sort of underlines and I think supports the idea that it's brain and brain function that we really define as life. So whatever it is that we identify as our, quote, self, brain function is critically important to it. And you can look at this when you look at the distribution in columns of at rest, light exercise, and strenuous exercise, beginning with skeletal muscle. So at rest, 1,200 mils per minute. Light exercise, and you basically over triple that. And strenuous exercise, you're basically sending about 10 times the volume of blood through the skeletal muscles that you did at rest, showing the overall impact of oxygen to skeletal muscle performance. Moving weight with your skeletal muscles consumes a lot of your energy. Therefore, that 10 times increase in blood flow. Likewise, the heart, 250 mils at rest is plenty every minute, but 750, we triple our cardiac output when we're exercising in a heavy way. But you look at this, the brain, 750 to start with, and constant all the way across. So mental operation, our awareness, our cognition, our learning, basically high blood flow at all times. The skin is involved in thermoregulation, and so from 500 mils at rest, and here we're assuming that you're resting under comfortable circumstances, but light exercise generates heat, strenuous exercise generates more heat, and so we're approaching 4 times the blood flow through the capillaries of the dermis in order to dump that excess heat. But look what happens. Do you need to make urine at a high rate in order to exercise? You really don't. And so you'll notice that the rate of blood flow to the kidney is much higher at rest, and it diminishes almost to half that rate under strenuous exercise. Digestion is what would be the main effects of abdominal viscera, and you can see again over a twofold reduction to all of the organs in the abdomen. And then miscellaneous other tissues basically get a reduction in flow. So when we relate this to what the heart is doing, here's that total cardiac output. And we see here under strenuous exercise, this would be up within the aerobic maximum, not our absolute total output. But we have achieved here almost a 3 times blood flow as at rest. So what happens when we have that accident and we puncture the skin? We're going to have a number of systems that respond. Certainly our clotting and inflammation system is going to respond to try to stop that blood flow, initiate healing, and eventually repair the damage. But the immediate problem at the time of injury is that of hemorrhaging, and the extent of the injury and the extent of the blood loss is what is the critical issue. We have an adjustment by the entire cardiovascular system to do a couple of things. First of all, the short-term effect is to maintain the blood pressure. Since it takes a matter of minutes for living cells to slow down and die when they're deprived of oxygen, that blood pressure on a whole body basis is essential. But then there are blood pressure adjustments, cardiac output adjustments, that are joined by longer term, and we are talking about a number of mechanisms, but we may, to restore the blood volume long term, it may work up to a week to 10 days to get back to a normal balance at rest. So short-term responses. To prevent that drop in blood pressure, we're going to detect the drop in blood pressure from hemorrhage if it's extensive enough. We're here not talking about a minor cut, but I don't know how many of you have ever witnessed an injury, but we routinely give away a liter of blood at blood donation drives, but I can tell you that a liter of blood on the floor looks like a lot of blood. At that point, we're starting to detect baroreceptors in those critical vessels here in the aorta and the carotid that we learned about, are going to be detecting that decrease and increasing the heart rate. At the same time, here's a wonderful secondary effect. The periphery begins vasoconstriction, squeezing those muscles to actually make the blood vessels smaller, especially on the vein side. The arteries are pulsing already. They have a lot of vasomotion as a result of being on the pressure side. But the vein side is relatively static. We can constrict those, decrease the volume of the vessel system as a short-term adjustment for blood pressure. The sympathetic nervous system will come in as a secondary effect, and it has a arterial constriction function that improves and increases the venous return. This sympathetic system is on top of this initial baroreceptor response. And finally, if we have a big enough hemorrhage, we are really activating the sympathetic nervous system, and we are seeing the appearance of epinephrine and norepinephrine as hormonal dumps from the brain, anti-diuretic hormone, which we'll talk about in a second, and also a cascade of hormones. The critical one for this is angiotensin II, but there's actually the release of something from the kidney called renin, which produces a cascade of angiotensinogen, angiotensin I, angiotensin II, aldosterone is the sequence, angiotensin II. All of these have a secondary effect of further supporting and increasing cardiac output and also increasing vasoconstriction. The long-term responses to hemorrhage were restoring blood volume, and that can take several days. One of the things angiotensin does, which is very important, is to increase your thirst. Although your hematocrit, the proportion of your blood that is blood cells, will go down with hemorrhaging, you can increase the pressure just by replacing the plasma. Drink a couple of quarts of water, and that will bring a short to couple of days response to blood pressure. Also, the balance of fluids between the living cells and their interstitial spaces, and the flowing blood, the plasma in the vessel system, will change. Osmosis will bring blood out of the interstitial spaces and back into the circulating blood, so that the circulating blood pressure is supported. Aldosterone and ADH are going to have broad-term effects, mainly in fluid retention and reabsorption. When we make urine, our kidneys can actually adjust to the amount of hydration we have. You know, if you sit down and you drink, say, 3 bottles of pop in a half an hour, then all of a sudden you have this big load of water, and your kidneys are going to make a high volume of low concentration urine to get rid of it. The same kind of thing applies when you're under water distress. We promote the kidneys to make low concentrations of very, very concentrated urine. Low volumes of concentrated urine. And although that's not adding to the fluid, we're going to use the thirst to do that. It is going to retain the fluids so that additional loss through urination is not going to be affected. The final effect, and this is probably the longest term effect, we are constantly making new red blood cells every day. So if you imagine a dial on the wall from 0 to 10, it's labeled red blood cell production. On a normal day when we're not injured, that'll be set at 2.5 or 3, cranking out red blood cells from the bone marrow. What happens when we hemorrhage? If we lose enough blood cells, we're gonna take that dial and turn it all the way up to 6, 7, 8, depending on how many blood cells we've lost. Now, the red blood cells take up volume in the blood, and what that does is raise the blood pressure. So this, as I said, will take a matter of days, but eventually it will restore the normal hematocrit and the normal blood volume. Oops, sorry. So I really do like these summary diagrams. Here's falling blood pressure and volume from hemorrhage. You can see the bleeding has reduced the blood pressure and blood volume. And here are our 2 responses. Our short-term response directed by the nervous system. We are going to experience pain, anxiety, and fear. We're basically going to get sympathetic stimulation out of that, the fight or flight reaction. The cardiovascular centers are going to respond to this pain, anxiety, and fear. The nervous system is also going to be transmitting sensory information from baroreceptors from our dropping pressure, and chemoreceptors from decreases in oxygen and increases in CO2 that are occurring in all tissues. That's going to stimulate this cardiovascular sympathetic complex, and here's what it produces. Peripheral vasoconstriction, mobilization of the venous reserve, and increased cardiac output. Those are all short-term. They can happen in a matter of minutes, and they all point toward rising blood pressure. Now, here on this inner circle, we have that long-term response, and it's going to be responding to the bleeding that stimulates the endocrine system. And here is a list of the hormones, the ADH, angiotensin 2, and aldosterone, all of which affect thirst, fluid retention, and EPO affects red blood cell production, which is going to, in a matter of days, increase retained fluids as we increase the blood sediment, the cells. Together, assuming you've stopped the bleeding, blood pressure and volume rise, and you restore that normal blood volume. Now, if you lose enough fluid, you experience a thing called shock. The driving force of shock is that essential nature of oxygen. So hypoxia, or low oxygen, is going to be driving this. Below 90 millimeters of mercury, we call that hypotension, which is an acute condition. We experience cool and clammy skin, which is an odd combination. Normally, when we have wet skin, it's because we have heat in the body we're trying to dump. But vasoconstriction for hemorrhage is driving the blood more to the core and away from the surface of the skin. So the skin feels cool, but sweat is being dumped as a result of sympathetic stimulation. And so that's what cool and clammy means. If we decrease blood flow to the brain, it can result in confusion. Shock can progress to unconsciousness. If the heart basically begins to be deprived of blood, the pulse can become weak. There's not much blood to pump. It experiences, though, a great acceleration, so it's rapid. Urine production decreases to near zero. And also, anything that's hypoxic, deprived of enough oxygen to produce ATP at the highest rate, is going to use those glucose molecules to make ATP by glycolysis. That's going to leave lactic acid in the tissues, increasing at a very rapid rate from anaerobic reproduction. And that means also then that there will be some, later on, some pain and a reaction we call acidosis. As we progress, we lose more and more. If the shock affects the heart, it can damage the heart muscle and can interrupt the normal heart rate. Obstructive shock results from blocking a blood vessel by a variety of things. We talked about plaque forming in blood vessel, but cardia tamponade is when fluid builds up in the pericardial space. When you do that, it's going to increase the pressure on the outside of the heart so it can't fill the same way. Or a pulmonary embolism is a blockage of flow to blood to the lungs. If we lose a lot of blood, what we do is we lose control of the ability to direct the blood to the part of the body that needs it. And that's called, when it's being distributed correctly, that's called vascular tone. That means that your cardiovascular system is operating in balance. And distributive shock results when you get circulation deprived of blood, and can basically damage various parts of the body like the brain stem or sympathetic nerves. That's called neurogenic shock. If there are excessive release of vasodilators, it means that all of a sudden some part of the cardiovascular system is relaxing. So whatever pressure there is expanding that, and it can produce septic shock or anaphylactic shock, both of which are dangerous. If blood volume drops more than 20%, hypovolemic shock results. Progressive shock occurs below 35%, above 35% loss, and this is where myocardial damage is likely. The reversible shock comes when we start to lose control of those smooth muscles. Basically, blood is pooling or is flowing to places that don't really maintain life. And this is where we would call it cardiovascular collapse, and blood flow stops and tissues begin to die. The final question we posed is what happens to develop the cardiovascular and circulatory system? How is it that a multicellular fetus develops a cardiovascular system and starts it working. This is not the typical method for organ systems. So, for example, although we're developing lungs in the fetus, they are collapsed. There are observations of fetal breathing, but that's an occasional muscle contraction that draws in fluid and expels it. There is no ongoing oxygenation going on. Likewise, we're developing things like kidneys, like stomach and digestive tract, that we're not using. However, from the time the embryo is relatively small, identifiable as a human embryo, the heart of the fetus starts to beat because it is necessary to circulate blood on the baby's side in order for the fetus to develop. And I want you to think about that language. When we have conception and implantation, we're going to develop tissues on the mother's side that are going to continue to process her blood and place that blood in a flow pattern through a new tissue called the placenta. Her organs are going to oxygenate that blood, fill it with nutrients. Her organs are going to clean out wastes and provide it into an exchange zone from the placenta. On the baby's side, we're going to set up a capillary network that will absorb that oxygen and will absorb those nutrients, basically draw them across, and circulate them through the fetus side. It is the fetal heart that is going to provide the force to move that material around the fetal tissue and the associated maternal tissues that must accompany development. Now here's a full-term fetus. Over here is the placenta. So this is a picture of the baby's side circulation. The branching red and blue strands show you where the capillary beds are placed. Now, I want to emphasize there is no direct blood flow from the mother to the baby. There is an exchange zone where the mother dumps oxygen and nutrients into this space. They are absorbed by the flowing blood of the capillaries of the placenta and directed down this umbilical cord into the fetal body. Now this red vessel that is carrying that material is carrying it toward the baby's heart. Now you'll notice it's oxygenated, so it's functioning sort of like a pulmonary vein, and it actually attaches to a special region in the liver, a venous network called the ductus venosus. It dumps the oxygenated blood there where it's collected and is shunted through this vein, the vein that becomes the hepatic vein, to the inferior vena cava. So the oxygenated and nutrified blood is flowing in through the umbilical vein, the ductus venosus, and which is, by the way, strictly a fetal, a gestation tissue, and up through the inferior vena cava into the right atrium. Now, there's an odd and different morphology in this developing heart. There are 4 chambers, as you can see, but those chambers are linked by openings. The first opening is shown here, the ductus arteriosus. So if you look at the pulmonary trunk just before it splits into the pulmonary arteries, there is an opening called the ductus arteriosus that attaches in a lake position in the aortic arch. So these two are actually one vessel at this point in development. The other connection, which I will show on the next slide, is the foramen ovale. The right atrium is connected to the left atrium. So this upper arrow comes out over here, you can see, so that the 2 atria are connected. So the blood flows in returning from the baby's body. You notice this blue vessel returning and joining with the oxygenated blood from the mother and the placenta into the right atrium and filling the right and left atrium together, then filling the right and left ventricles together. When the ventricles contract, they basically expel the blood then into a common area. So they're expelling through this vessel, and there is a connection here. This is the ductus arteriosus connection above. The filling port between the right and left atrium is called the foramen ovale, the opening that's oval, and it is open in the fetal heart. So this heart is pumping. It is contracting to propel blood all around, but the main issue is supplying the dividing and differentiating cells. There's not that much function going on out here. So when we have this system, you can see that the returning blood circulating around the body. From above, we're going to return it to what will become the superior vena cava, to the right atrium. From below, there is a double connection down here of umbilical arteries in what is called the internal iliac artery, and it draws this deprived or depleted blood off. This double braid of umbilical arteries is carrying depleted blood up the umbilical cord to the placental capillaries. So this is actually the conformation of that cardiovascular system in the full-term fetus. When the fetus is delivered, there is a big shift in pressure when you clamp off the umbilical vessels. Now they're going to basically atrophy, but that change in pressure will cause a constriction of this duct, and blood vessels often constrict and form fibrous tissue and no longer carry blood. That closes off the flow from the pulmonary trunk and aorta that is between those. A shift in pressure then from the clamping off of the umbilical blood supply causes this right side of the heart to pump blood at full pressure into the pulmonary trunk and arteries and basically inflate the cardiovascular system in the lungs. At that point, the baby taking its first breath produces a very different environment around the capillaries, and oxygen delivery through the baby's system has commenced. When that closure occurs, there is a flap on the foramen ovale that basically flaps down and quickly adheres, closing the connection between the right and left atria and isolating these two circuits. So now we have the right side lung and left side body double circuit established. This is normally occurring right at the point of delivery. Now there's a number of factors controlling overall cardiac output. We've now put all of these systems together. We know we have autoregulation, which basically can make adjustments around the body with vasomotion. And autoregulation can also establish the regular at-rest heartbeat and also detect the changes that can adapt to things like light exercise. Neural mechanisms, which are hooked in with our eyes, our ears, our smell, our taste, all of those sensory, we're surveying the outside world. We're sensing temperature. And so we're basically getting a lot of nervous signals about what's going on around us and what should we do. Here's how we respond quickly with adjustments. For example, probably the most extreme is a fight or flight adjustment. Something's convinced us that we have to run away or fight for our lives, and neural mechanisms contribute to that. With the endocrine system, we're well aware that the neural and endocrine systems work together for a fight or flight, and ongoing regulations are often more assigned to the endocrine system than the neural mechanisms. So, for example, high blood pressure is something that is typically detected and reported by the neural system, but the long-term adjustment that makes that ongoing is heavily involved in the endocrine system. Let's take a look at some of these factors, and as study aids, these diagrams are really well placed. Autoregulation, showing here what can disturb homeostasis and affect blood pressure and volume. Well, physical stress, trauma, alarm, threat, high temperature, which basically tells you you have to behave differently right now. Chemical changes inside the body, like oxygen or CO2 levels, and increased tissue activity like exercise. These basically, within a certain range, will work through cardiac output and vasomotion to keep homeostasis in place. But what happens short-term and long-term when we exceed that auto-regulation, that normal flux that we encounter? Neural mechanisms are going to be sensitive to changes of blood pressure, especially, and blood chemistry, mostly oxygen and CO2. It's going to work through the cardiovascular center, and short-term adjustments are going to make that response quick. Endocrine is a little slower. This is showing the kidney with the adrenal gland perched on top of it. Endocrine response is not as fast as neural, but in fact, it's still pretty quick. A good fight or flight reaction, a good alarm situation, you're going to start to feel your heartbeat within 15 or 20 seconds. That's not very long. This is going to adjust blood volume and pressure to restore homeostasis. Let's look at several of these examples. So this is from the carotid and aortic sinuses. If we're looking at increasing blood pressure, we're looking at a baroreceptor. It's going to work through those brain stem centers to inhibit or accelerate the heartbeat, and through the vasomotion center to allow for vasodilation, decreasing the local resistance will increase the flow to specific tissue and bring your blood pressure back down. When we look at baroreceptors working the other way, a drop in blood pressure, we get the same centers stimulated in opposite ways. So we're going to stimulate accelerating the heart and inhibiting the heart. We're going to constrict the blood vessels. All of these contribute to increasing the blood pressure. Chemoreceptor reflexes have an interesting combination here, and I want you to look where the pointer is right now, because these three things occur together. Oxygen and CO2 are always related. Oxygen low, CO2 high occurs under a number of circumstances. However, CO2 is linked to pH. By that I mean, if you produce CO2 in a water solution, it forms a thing called carbonic acid. That carbonic acid dissociates and is now bicarbonate and hydrogen ion. That means the acid goes up whenever there's CO2. Acid goes up means pH goes down. So these things are connected. if we see an increase in CO2, but low pH, lowering pH and oxygen, the chemoreceptors are going to work through these cardiovascular nervous elements to increase cardiac output and pressure and constrict the blood vessels. That's one effect that's going to move more oxygen in, more CO2 out, and increase the pH. But a second thing that happens in conjunction with this is stimulating the respiratory centers to breathe harder. That's going to get rid of CO2 faster, bring oxygen in faster, and basically correct the imbalance. When we look at blood pressure and volume decreasing, hormonal regulation can act long-term, as we just summarized earlier. Renin, and the cascade is renin, angiotensinogen, angiotensin 1, angiotensin 2, and aldosterone. ADH is also released. Erythropoietin is also released under this kind of stimulation. So the effects here: you get thirsty, you drink. You retain water, so the blood pressure drop is arrested. You also, through these hormonal effects, increase peripheral vasoconstriction. The blood vessels and the blood volume of the vessels gets smaller, and pressure is held or increased. Long term, what we're doing is increasing red blood cell production, and over a period of days, the volume of the blood through the hematocrit is increased. Sympathetic activation, epinephrine, norepinephrine, is having an effect short term on this cardiac output and peripheral vasoconstriction. So many systems. You see the importance here of oxygen delivery and of blood pressure. Cells die in a matter of minutes. And so there's short-term and long-term responses, but layered responses in order to adjust the body. An interesting hormone, natriuretic peptide, a really interesting name, natrium, the root of natri, is the Greek word for sodium. That's why sodium is Na on the periodic chart. Uretic, uresis refers to water loss. Diarrhea refers to water loss. Uresis essentially refers to loss. So this is basically a peptide that controls the movement or loss of sodium. We call them ANP and BNP. They are both produced in the heart, and they respond to excessive diastolic stretching. If the pressure is approaching or at the upper limit for the heart, excessive blood pressure is a problem. And the response would be to do what? Lower the pressure or lower the blood volume and reduce the stress on the heart. This is where natriuretic peptide comes in. Interestingly enough, its effect to decrease high blood pressure and volume is just to counteract the effects of all the previous hormones we've talked about. So when natriuretic peptide is released by the heart, it increases sodium loss in the urine, and because of osmosis, more sodium in the urine means more water is drawn over. One of the quick ways of lowering blood pressure is just lower the volume of the blood. Thirst is decreased, so you stop drinking. It also inhibits the production of all of those other hormones. ADH, aldosterone, epinephrine, and norepinephrine are all inhibited by this natriuretic peptide. And finally, its effect on the periphery. We've got high blood pressure. Let's just dilate the blood vessels, make the volume of the system more, and blood volume will decrease. As we look at the body and how it operates with all of these systems, you kind of got to ask the question, where does the blood go? And this control is adjusted on a hypoxia basis, on an exercise basis, on an emergency basis. But we want to make a couple of points about these three places: the brain, the heart, and the lungs. The blood flow to the brain is the top priority. There is no adjustment that cuts down blood flow to the brain. If blood flow to the brain is interrupted, it results in a stroke, a life-threatening situation. This is called a cerebrovascular accident. As I said, blood flow to the brain under normal, healthy circumstances is constant and at a high level. Blood flow to the heart. The heart is constantly working. The coronary arteries and the cardiac vessel system make sure that that is maintained on a high level. High exertion means an increase of blood flow through the myocardium. Overexertion means lactic acid, which will dilate coronary vessels and increase coronary blood flow. Epinephrine is also another thing that dilates coronary vessels, increases the heart rate, and strengthens contractions. We have made note of the fact of what happens when you block blood flow to a portion of the heart, and of course that's some kind of cardiac event. Heart attack is a blockage, and it can be progressive. If you experience a minor blockage so that a section of the heart wall goes anaerobic, lactic acid is being produced, it can result in a pain effect. You're basically putting acid in a muscle, and the nerves say, wow, that hurts. It's called angina, although angina does not always precede a full cardiovascular event. As you deprive oxygen, more and more tissue can be damaged or even die, and death can result. Blood flow to the lungs is regulated by the oxygen levels in the blood to the exchange unit. This is called an alveolus, singular, or they are called alveoli. These are little pockets in a little organ that looks like a bunch of grapes, very thin walls covered with capillaries. If the blood in the region has high oxygen, then those vessels dilate and fill the local capillaries. If it has low oxygen, then those vessels constrict, and basically blood flow is reduced through those vessels. Aging of the cardiovascular system is predictable as tissues get old and pass from that middle-age maintenance to geriatric condition. In the blood, we're going to see a decrease in the proportion of the blood that is blood cells, the so-called hematocrit. That's an aging effect. We also see the formation of blood clots, which are normal for repair, but in a middle-aged person or younger, typically do not occur in the circulating blood. We see more and more clots forming with the decline of tissues in an aging person. Another effect is the pooling of blood in the legs as a result of the lessening of the efficiency of venous valves in retaining the blood and assisting the lifting of blood back to the heart. Now, in the heart, we're going to see declines in cardiac output, changes in the conducting system. So this is where pacemaker replacement becomes important. The elastic nature of the connective tissue that forms the cardiac skeleton is decreased, as is all elastic tissue, cartilage and elastic fibers, reticular fibers, all begin to be stiffer. All vessels in the body start to clog up, and this occurs in the heart. And finally, the regions of the heart that are damaged, local regions, we see a replacement by scar tissue, which is less elastic. So the general picture that we saw for muscles also applies to myocardium. Finally, the blood vessels, they lose their elasticity, their ability to move. That's as a result of the connective tissue in them, the elastic tissue, but also the loss of smooth muscle mass. Pressure changes can cause aneurysms, little places where the artery wall bulges out with the heartbeat and eventually can break. Calcium deposits, for some reason, as little black spots, start developing on vessel walls. And they can cause strokes, they can cause cardiac infarctions. And clots, thrombi can form around the atherosclerotic plaques that are developing throughout the system. So actually we have now covered the cardiovascular system.